about these three scenarios that I mentioned previously, and just to introduce the notation, the interval of convergence. Of a Taylor series. So the interval of convergence is the set of all x values for which the Taylor series converges. And this is always a symmetric interval, or at least this interval will always take on the three green highlighted forms that I have above. And so the three cases are that the interval might be, as in case 1 here, it might just be a single point, so x equals 0. It might be the case of the interval from minus r to r here, and in that case there are three possibilities. I think actually 4 possibilities. It could be minus r to r, not including either of the endpoints. It could be minus r to r, including the left endpoint but not the right. It could be minus r to r, including the right endpoint but not the left, and it could be including both intervals, minus r to r. The third case is, we could write it as x is all real numbers. I like to sometimes say, the interval of convergence, let's just write all real numbers. So these three scenarios connect with the three pictures that I drew above. So here's scenario 2, and here's scenario 3. And it would be scenario 2, only one of these 4 possibilities would be true. And you would individually test the endpoints to decide which one. Okay, so the next block of material is just, now that we understand what a Taylor series is and how to compute it by differentiation by hand, and how to understand where it converges, there are a number of shortcuts, ways of working with Taylor series that are really useful. So I want to go through several different examples for you, and then we'll talk about using Taylor series to evaluate, to make approximations. So that's a little bit like when we used, in preview activity 8.3.1, we used Taylor series, or at least the ideas of Taylor series, to approximate the number e. And so we'll be talking about that. And then the third thing we'll do is I'll just show you an example of a Taylor series that converges but does not converge to the original function. Okay, so let's start with manipulating Taylor series. So we had the example 1 over 1 minus x, and this is the sum from k equals 0 to infinity of x to the k. So it's one of our simplest series. It comes from really the geometric series. Right, so you'll recognize this. The interval of convergence is minus 1 to 1 is the interval of convergence. as we computed in the last video. So so you can substitute into Taylor series that are known. So here's an example with substitution. If I want to know something about the Taylor series that we approximated in the Maple demo that I did not talk about, so we computed Taylor series for e to the x and sine of x, but you'll recall in the Maple demo we investigated the function 1 over 1 plus x, and I said I was going to hold off on that one. So here it comes again, and so notice that 1 over 1 plus x is equal to 1 over 1 minus negative x, right? And so this is actually now in the form of a function 1 over 1 minus x that we had earlier, except that instead of x we have minus x. And so we can actually just substitute in to the Taylor series for 1 over 1 minus x and say that this is the sum from k equals 0 to infinity of minus x to the k. This is kind of cool. So let me go back up above and just write out what some of these terms are for 1 over 1 minus x. So we have 1 plus x squared plus dot dot dot. Okay, so if I want to write out the terms of this new Taylor series, they are going to be 1 minus x plus x squared minus x cubed, and so on. And so this new interval of now this is a Taylor series of 1 over 1 plus x. So here is the Taylor series for 1 over 1 plus x. Now, once we have this Taylor series, we might want to know the interval of convergence. So I'm going to go ahead and compute the interval of convergence. We're going to just kind of use a shortcut here. We know that the original series converges when x is between minus 1 and 1. So our new series should converge when negative x is in the interval minus 1 to 1. In other words, when x is, well, it doesn't actually change, but when x is between minus 1 and 1. So here's our new interval of convergence, and we have a Taylor series for 1 over 1 plus x. Okay, so there are a number of other things we can do here. Once we have the Taylor series for 1 over 1 plus x, we could do another substitution. So here, let me just go ahead and label my examples. Here's another example of substitution if we want to know the Taylor series for 1 over 1 plus x squared. Right, and now here I have a Taylor series for 1 over 1 plus x, and so I could just plug in x squared everywhere I see an x in the preceding Taylor series. So we could write the sum from k equals 0 to infinity of negative x squared to the k. And here, if I want to write out a few of the terms, we would have 1 minus x squared plus x to the 4th minus x to the 6th plus dot dot dot. and this is going to converge when x squared is in the interval -1 to 1. This, again, this just means in. Shorthand for is an element of. And when x squared will be in -1 to 1 is going to happen when exactly when x is in -1 to 1. Okay, so as another very, very similar example here, right? Example 1 over 1 minus, let's say, 2x, right? Now, we would be thinking about this as the sum from k equals 0 to infinity of 2x to the k, right? So equals the sum k equals 0 to infinity of 2 to the k x to the k, right? And if we're writing out just a few of the terms, we have 1 plus 2x plus 4x squared plus 8x cubed plus ... Okay, and then the question is, where does this converge? And this should converge when 2x is in the interval -1 to 1, or in other words, when x is in the interval -1/2 to 1/2. Okay, so there's a few examples. Let me go ahead and do a different type of example. So here's where if you are obtaining, you can obtain, if you can obtain an expression for a function you're interested in by substitution into another Taylor series. This type of method works, and then you can trace through where convergence, where the interval of convergence should be. Another example would be taking derivatives. So we can actually do calculus operations. So you can also integrate and differentiate. So here's an example. So we know that let's consider the example 1 over 1 minus x. We know that Taylor series very well. So if we differentiate 1 over 1 minus x, we end up with 1 over 1 minus x squared. So let's try to find the Taylor series for 1 over 1 minus x squared. One option would be to actually differentiate, find all these derivatives of this function, and compute by hand the Taylor series as we did way up at the beginning, right up here, using these kinds of formulas for the Taylor polynomial. On the other hand, we don't really need to do that. I apologize for all the scrolling here. We don't really need to do that because we can actually differentiate term by term the Taylor series for 1 over 1 minus x. So we know that 1 over 1 minus x is just this series right here, the sum of x to the k. And so we want to differentiate that. So this is equal to the derivative of the series for 1 over 1 minus x. And so I'm going to go ahead just and write out all of those terms. Let me get another page in here. And now it's true, although not actually obvious, and in higher level mathematics courses, you'll gain some more tools for proving that you can actually switch the order of this infinite summation that we're doing here and the derivative. So both of those are limiting processes, and switching the order of limiting processes is actually something that one in general needs to be careful with. It's okay in this case, and so we're going to go ahead and just use that result. So if we start just taking derivatives here, the derivative of the first term is 0, plus derivative of the second term is 1, the derivative of the third term is 2x, plus 3x squared, plus ... And so if I want to write this with summation, we'll sum from k equals 0 to infinity of k plus 1 times x to the k. And so it turns out that that this is the Taylor series for 1 over 1 minus x squared. And in this case, the interval of convergence is from -1 to 1 as well. As a quick example of integration, so we happen to know that our series over here, 1 over 1 plus x squared, so now we know what that series is. So the integral of 1 over 1 plus x squared dx is equal to arctangent of x. And we know the series for 1 over 1 plus x squared. So the series for arctangent of x is equal to the integral of, and here we have negative x squared to the k. Oops, what just happened? K equals 0 to infinity. And
So I'm going to just write out some of the terms. I like to do that. It just helps me avoid making mathematical errors. So we want to have the integral of, okay, so for k equals 0, we just have anything to the 0 power is 1, and then minus x squared plus x to the 4th minus x to the 6th plus ... Okay, I'm running out of room here, so I'm going to go ahead and just get rid of a few terms here. Minus ... and then I want to put my dx in here. All right, and so now it turns out that, again, it's not a trivial operation to integrate both sides. To switch the limit, the integral and the summation. But we can go ahead and just integrate every term here. And so what we end up with is x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus ... Okay, and because I am taking an antiderivative, we should make sure that we add our constant of integration. And so I'm going to go ahead and just do that at the front. I don't want it to get lost after the ... Another reason for adding it right at the front there is that that's where the constant term would normally go. So what we then need to verify is to find C. Note that arctan of 0 is equal to 0, so the angle with a tangent of 0 is equal to 0. If I plug in 0 for all the x's, then all of those terms drop out, and we end up with C equals 0. Let me go ahead and add just one more page here. Hence, the series representation of arctan of x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus ... This holds for x in minus 1 to 1. Okay, so there is that example, and so let me just go ahead and use this, and so now just kind of moving into this second bullet point here, we can actually use the Taylor series to evaluate infinite series and also to make approximations. So let's try the following example. So notice that arctan of 1 is equal to pi over 4, right? The angle with a tangent of 1 is pi over 4, right? So that's the angle where we have a triangle with the two sides here of equal length. And so now we can use this. So notice that the series representation, so So pi over 4 is equal to arctan of 1 is equal to 1 minus 1/3 plus 1/5 minus ... Okay, and so it turns out that in fact we could approximate pi over 4 using this sum. We could also approximate pi is equal to 4 times arctan of 1. And so there we have 4 minus 4/3 plus 4/5 minus 4/7 plus ... Okay, so here's a series representation. So pi is actually equal to this product. And notice this is an alternating series. And the terms go to 0. We know it's a converging series because we have shown that this should converge. And so, well, actually, here's a question that we should be careful about, which is whether this actually does converge at the endpoint 1, and so in fact it does. And the reason is because we have an alternating series whose terms decrease to 0. So in fact, in this particular example, we will end up having the interval of convergence being the closed interval from -1 to 1. So this series does converge, and moreover, so we can use the alternating series estimation to take a finite number of these terms and get an approximation of pi to any degree we like, and so that's kind of a fun one, because you could without too much trouble just plug several of these terms in and approximate pi. Okay, so I'm going to